Hi guys, Dr. Burns here. We're going to start chapter 8 today, which is on a topic called hypothesis testing. I love this chapter. I think this is a really important topic. If you do end up going into any kind of a field where you have to do research, or you go to grad school and you have to do a master's thesis, or even as an undergrad, you may do some research. It's very common to use hypothesis testing, especially in the social sciences. And so I want to really get a good feel for what we mean by hypothesis testing and how it works. Make sure your cell phones are put away and you're ready to take notes and listen for the next few minutes. So we're starting off with what is a hypothesis test and what does it involve? The objectives for this section is to be able to conduct a hypothesis test involving one population proportion for sure, possibly two later on if we have time. Be able to write a null and an alternative hypothesis for a test involving a population proportion. And then to compute and interpret a test statistic and its associated p-value. And we'll talk more about that in this section and the coming sections. So first of all, what is hypothesis testing? What is the point of it? It's a procedure that enables us to choose between two hypotheses, just like in science class, two hypotheses or statements when we have variability in our measurements. So in other words, if we think a population proportion is 30%, for example, and then we pull a sample and find that it's 40% in our sample, what we want to do is decide, do we think the 30% figure is still true, or do we think it has changed? So it's like you're making two claims and you're choosing between those two claims. Any field where we are looking at observations and we're pulling samples and having to make decisions about those samples and what that tells us about the population proportion might use a hypothesis test. A quality control engineer may hypothesize that a new assembly method produces only 5% defective items, and so they want to test out that claim. And so they pull a sample to do that and make a comparison. In education, they may compare two methods of teaching. A political candidate may claim that a plurality of voters, over 50%, favor him in an election. In psychology, they might pull a sample and look at what percentage of the sample agreed with a certain statement, for example, and compare that to a previous data where they did the same research to see if anything's changed. There's four general steps when we talk about hypothesis testing. The first is to hypothesize. So hypothesize, actually make your hypotheses, and that's what we're going to focus on in this section. State your claim that will be weighted against some other neutral skeptical claim. So we'll have what's called a null and an alternative hypothesis. The next step is determine how you'll use your data to make your decision and make sure you have enough data to minimize the probability of mistakes. So I think what I intended for you to say here was to check conditions. So in other words, make sure the central limit theorem applies. Prepare and make sure you have what you need to correctly run your hypothesis test. The next step is to compute, gather your data, and then compare it to your expectations. So you'll run a computation. We're going to use StatCrunch to help us with that computation. And then finally, we're going to state the conclusion based on what we find. So the fourth step would be to interpret. So these are the four basic steps we're going to follow every time we run a hypothesis test. Let's look at a quick example here. Suppose a coin is spun on a flat surface. You hypothesize that it is more likely to come up tails because that side of the coin bulges out slightly compared to the head side. So think about it. If you spin the coin 20 times, all right, if it's truly a fair coin, how many of those times would you expect it to land on tails? Well, you would expect it to land on tails half of that, or 10 times, right? Instead, though, it ended up landing on tails all 20 times. If it had truly been a fair coin and it was equally likely that it would land on heads or tails after spinning, this would be very strange or very unusual, right? That all 20 flips ended up with 20 tails. This is so unusual that you would conclude that your hypothesis that the coin was more likely to come up with tails was correct. So let's kind of walk through how those 4 steps would have applied here. So step 1 was to hypothesize that the coin is more likely to come up tails against the neutral hypothesis that it's a fair coin. 2 is to estimate. In this case, it would be to estimate the proportion of tails in 20 spins proportion of tails in 20 spins that we get, and we would estimate how many. We would estimate that we would get 10, right? 10 out of 20 would be on tails. That's sort of what we would assume would happen. We actually spin the coin. So we spin the coin 20 times and observe the results. And like I said, if it had been a fair coin, we would have expected about 10 of the spins to land on tails. However, we got all 20. So then we would decide that, let's see, it would be unusual. It would be so unusual or unlikely, let's say, to get 20 tails in 20 spins if the coin was equally likely to land on heads or tails when spun. That means we conclude. So it's kind of like you're making a decision based on what you're seeing in your sample, in your observation. We would conclude that the coin is more likely to land on tails when it's spun. When you set these up, you're going to set up your hypotheses first. So you have a pair of hypotheses called the null and the alternative hypothesis. The null is the neutral. Another way of thinking of it is the status quo. It's the skeptical statement about the population parameter. And it always contains an equal sign. Notationally, we would write H0 colon P equals some population parameter that we want to compare it to. So I'm going to call that P0. The alternative is what you want to test. That's also called the research hypothesis. It would always contain a less than, a greater than, or a not equal to. And so the format for that would be H sub A, and then P, and then it could be, like I said, one of these 3 symbols, maybe does not equal to, P not, or greater than, or less than. Hypotheses are always about the population parameters. That's very important. We would never involve p hat when we write our hypotheses. We always use the population parameter that we want to compare to. The null hypothesis always gets the benefit of the doubt when we're going through the procedure. We only reject the null hypothesis if what we see in our sample or observed outcome would be extremely unusual if the null hypothesis were true. Kind of like our coin example. If I got 20 tails on 20 spins, something is unusual about that coin. It's analogous to assume that somebody in a trial is innocent until proven guilty beyond a reasonable doubt. What type of hypotheses we have, or alternative rather, determines whether we have what's called a one-sided or a two-sided hypothesis. Our null hypothesis always takes this format. If it's an alternative hypothesis that's two-sided, it's going to look like this. H sub A would be P does not equal P not. So when you have the not equal to, that's your two-sided hypothesis. If you've got a one-sided but a left-tailed hypothesis, that's your less than case. And then if you've got a right-sided hypothesis, your alternative would be P is greater than. That's your greater than case. So let's do a quick example here. During the previous fiscal year, 10% of the orders placed at Firehouse Subs were done so online. In an effort to increase this percentage, Firehouse Subs has purchased ads on Facebook and Twitter. Firehouse Subs gathers data on types of orders placed on a sample of 20 days during the current fiscal year. The question is, has there been a change in online orders? That research question is going to drive your alternative hypothesis. Let's start with the null. So the null hypothesis is that nothing has changed. It's still the status quo. P is still 10%. Nothing has changed. Your alternative based on the research question, a change means it could be higher or lower. So we're going to say P is not equal to 10%. Is this one-sided or two-sided? Well, it's the not equal to case, so that would be two-sided. What else could the retailer have posed? I think maybe a better alternative would have been have sales increased. If we had done an increase in sales online, then they would have said is P greater than 10% and would have done a right-sided test. I think that might have been a better research question, but this one works as well. Our test statistic, that's the next thing I want to talk about. Our test statistic compares our observed outcome, so I'm going to also put underneath that our sample outcome, with the outcome we would have expected to get if the null hypothesis had been true. When that test statistic is far away from what we expect, the P naught, then we reject our null hypothesis and we conclude that we think that the evidence is supportive of the alternative hypothesis. What does the test statistic look like? So our test statistic is going to have this structure. We usually use Z again for our test statistic, and that would be, it's going to be the observed value minus the expected or the null value divided by the standard error. And what I hope you maybe kind of recognize is that this has the same structure as this. Remember way back when we calculated z-scores, we used this structure. It was our particular value we were working with, that was x, minus the mean, the mu, divided by sigma, the standard deviation. So observed is p hat. So in other words, that becomes z equals p hat minus the null value of P naught divided by our standard error. And our standard error, remember, is going to be the same formula we had in Chapter 7. It's going to be the square root of, now I'm using P naught instead of P, but it's the same idea. It's what we would use with our null hypothesis. P naught times 1 minus P naught divided by N, where N is our sample size. P hat is the sample proportion we get from the data, and P naught is the proportion we use with the null hypothesis. So based on this test statistic, we're going to calculate what's called the p-value. So the p-value is the probability of seeing our particular sample P hat if we expected that the null was true. The null hypothesis tells us what to expect when we look at our data. If we see something unexpected with P hat, that is, if we are surprised, then we should doubt the null hypothesis. If we are really surprised, then we should reject the null hypothesis. And I'm going to put reject H naught, the null hypothesis. The p-value gives us a way to numerically measure how surprised we are. It's the probability, and I really like this definition, it's the probability that if the null hypothesis were true, our test statistic will have a value as extreme or more as what we actually observed with P hat. Small p-values mean we are surprised, whereas large p-values mean we are not surprised. So we reject the null hypothesis when we have small p-values. Finally, the significance level. The significance level is the probability of making a mistake, of rejecting the null hypothesis when, in fact, H naught is true. The symbol we use for the significance level is alpha. And for most applications, we're going to use 5%, but sometimes we could use 1% or 10%, depending on what the question specifies. Last little point, if we get a p-value that is smaller than our significance level, our p-value is small and we reject the null hypothesis. On the other hand, if we get a p-value that is larger than our significance level, then our p-value is not small, we are not surprised, and we fail to reject the null hypothesis. I know there's a lot of information. Hang in there. We will go over this again in class and do plenty of examples. So bring your notes with you, and I'll see you tomorrow.